In the last video, we talked about different ways to represent the central tendency, or the average of a data set. What we're going to do in this video is to expand that a little bit to understand how spread apart the data is as well. So let's just think about this a little bit. Let's say I have negative 10, 0, 10, 20, and 30. Let's say that's one data set right there. And let's say the other data set is 8, 9, 10, 11, and 12. Now, in both, let's calculate the arithmetic mean for both of these data sets. So let's calculate the mean. And when you go further on in statistics, you're going to understand the difference between a population and a sample. We're assuming that this is the entire population of our data. This is the entire population of our data. So we're going to be dealing with the population mean. We're going to be dealing with, as you see, the population measures of dispersion. I know these are all fancy words. In the future, you're not going to have all of the data. You're just going to have some samples of it, and you're going to try to estimate things for the entire population. So I don't want you to worry too much about that just now, but if you are going to go further in statistics, I just want to make that clarification. Now, the population mean, or the arithmetic mean of this data set right here, it is negative 10 plus 0 plus 10 plus 20 plus 30 over, we have 5 data points over 5. And what is this equal to? That negative 10 cancels out with that 10. 20 plus 30 is 50 divided by 5. It's equal to 10. Now, what's the mean of this data set? 8 plus 9 plus 10 plus 11 plus 12. All of that over 5. And the way we could think about it, 8 plus 12 is 20. 9 plus 11 is another 20, so that's 40. And then we have a 50 there. Add another 10. So this is, once again, is going to be 50 over 5. So this has the exact same sample. Well, no, let me be very close. They have the exact same population means. Or if you don't want to worry about the word population or sample and all of that, they have both of these data sets have the exact same arithmetic mean. When you average all these numbers and divide by 5, or when you take the sum of these numbers, divide by 5, you get 10. Some of these numbers divide by 5, you get 10 as well. But clearly, these sets of numbers are different. You know, if you just looked at this number, you say, oh, maybe these sets are very similar to each other. But when you look at these two data sets, one thing might pop out at you. All of these numbers are very close to 10. I mean, the furthest number here is 2 away from 10. 12 is only 2 away from 10. Here, these numbers are further away from 10. Even the closer ones are still 10 away, and then these guys are 20 away from 10. So this right here, this data set right here is more disperse. More disperse, right? These guys are further away from our mean than these guys are from this mean. So let's think about different ways we can measure dispersion, or how far away we are from the center on average. Now, one way, this is kind of the most simple way, is the range. And you won't see it used too often, but it's kind of a very simple way of understanding how far is the spread between the largest and the smallest number. And literally, you take the largest number, which is 30 in our example, and from that you subtract the smallest number. So 30 minus negative 10, which is equal to 40, which tells us that the difference between the largest and the smallest number is 40. So we have a range of 40 for this data set. Here, the range is the largest number, 12, minus the smallest number, which is 8, which is equal to 4. So here, range is actually a pretty good measure of dispersion. We say, OK, both of these guys have a mean of 10. But when I look at the range, this guy has a much larger range. So that tells me this is a more dispersed set. But range is always not going to tell you the whole picture. You might have two data sets with the exact same range, where still, based on how things are bunched up, it could still have very different distributions of where the numbers lie. Now, the one that you'll see used most often is called the variance. The variance. Actually, you're going to see the standard deviation in this video. That's probably what's used most often, but it has a very close relationship to the variance. So the symbol for the variance, and we're going to deal with the population variance. Once again, we're assuming that this is all of the data for our whole population, that we're not just sampling, taking a subset of the data. So the variance, its symbol is literally this sigma, this Greek letter squared. That is the symbol for variance. And we'll see that the sigma letter actually is the symbol for standard deviation. And that is for a reason. But anyway, the definition of variance is you literally take each of these data points, find the difference between those data points and your mean, square them, and then take the average of those squares. I know that sounds very complicated, but when I actually calculate it, you're going to see it's not too bad. So remember, the mean here is 10. So I take the first data point. I say it's, let me do it over here. Let me scroll down a little bit. So I take the first data point, negative 10. From that, I'm going to subtract our mean, and I'm going to square that. So I just found the difference from that first data point to the mean and squared it. And that's essentially to make it positive. Plus the second data point, 0 minus 10 minus the mean. This is the mean. This is that 10 right there, squared. Plus 10 minus 10 squared. That's the middle 10 right there. Plus 20 minus 10. That's the 20 squared. Plus 30 minus 10 squared. So this is the squared differences between each number and the mean. This is the mean. This is the mean right there. That is the mean. I'm finding the difference between every data point and the mean, squaring them, summing them up, and then dividing by that number of data points. I'm taking the average of these numbers, of the squared distances. So when you say it kind of verbally, it sounds very complicated, but you're just taking each number, how far, what's the difference between that, the mean, square it, take the average of those. So I have 1, 2, 3, 4, 5, divide by 5. So what is this going to be equal to? What is this going to be equal to? Negative 10 minus 10 is negative 20. Negative 20 squared is 400. 0 minus 10 is negative 10 squared is 100, so plus 100. 10 minus 10 squared, that's just 0 squared, which is 0. Plus 20 minus 10 is 10 squared is 100. Plus 30 minus 10, which is 20 squared, is 400. All of that over 5. And what do we have here? 400 plus 100 is 500, plus another 500 is 1,000. It's equal to 1,000 over 5, which is equal to 200. So in this situation, our variance is going to be 200. That's our measure of dispersion there. And let's compare it to this data set over here. Let's compare it to the variance of this less dispersed data set. So let me scroll over a little bit. So we have some real estate, although I'm running out. Maybe I could scroll up here. There you go. So let me calculate the variance of this data set. So we already know its mean. So its variance of this data set is going to be equal to 8 minus 10 squared plus 9 minus 10 squared plus 10 minus 10 squared plus 11 minus 10. Let me scroll up a little bit. Squared plus 12 minus 10 squared. Remember that 10 is just the mean that we calculated. You have to calculate the mean first. Divided by, we have 1, 2, 3, 4, 5 squared differences. So this is going to be equal to 8 minus 10 is negative 2 squared is positive 4. 9 minus 10 is negative 1 squared is positive 1. 10 minus 10 is 0 squared. You still get 0. 11 minus 10 is 1 squared. You get 1. 12 minus 10 is 2 squared. You get 4. And what is this equal to? All of that over 5. This is 10 over 5. So this is going to be, all right, this is 10 over 5. 10 over 5, which is equal to 2. So the variance here, let me make sure I got that right. Yes, we have 10 over 5. So the variance of this less dispersed data set is a lot smaller. The variance here, the variance of this data set right here is only 2. So that gave you a sense. That tells you, look, this is definitely a less dispersed data set than that there. Now, the problem with the variance is you're taking these numbers, you're taking the difference between them and the mean, then you're squaring it. It kind of gives you a bit of an arbitrary number. And if you're dealing with units, let's say if these are each negative, well, let's say these are, let's say their distances. So this is negative 10 meters, 0 meters, 10 meters. This is 8 meters, so on and so forth. Then when you square it, you get your variance in terms of meters squared. It's kind of an odd set of units. So what people like to do is talk in terms of standard deviation. Standard deviation. Standard deviation, which is just the square root of the variance. It's just the square root of the variance, or the square root of sigma squared. And the symbol for the standard deviation is just sigma. So now that we figured out the variance, very easy to figure out the standard deviation of both of these characters. The standard deviation of this first one up here, of this first data set, is going to be the square root of 200. Square root of 200 is what? The square root of 2 times 100. This is equal to 10 square roots of 2. That's that first data set. Now, the variance of the second data set is just going to be the square root of 2. Variance is going to be the square root of that. Sorry, the standard deviation of the second data set is just going to be the square root of its variance, which is 2, which is just 2. So the second data set has 1/10 the standard deviation as this first data set. This is 10 roots of 2. This is just the root of 2. So this is 10 times the standard deviation. 10 times the standard deviation. And this, hopefully, will make a little bit more sense. Let's think about it. This has 10 times more the standard deviation than this. And let's remember how we calculated. Variance, we just took the each data point, how far is away from the mean, squared that, took the average of those. Then we took the square root, really just to make the units look nice. But the end result is we said that that first data set has 10 times the standard deviation as the second data set. So let's look at the two data sets. This has 10 times the standard deviation. 10 times the standard deviation. Standard deviation. Which makes sense intuitively, right? I mean, they both have a 10 in here, but each of these guys, 9 is only 1 away from the 10. 0 is 10 away from the 10, 10 less. 8 is only 2 away. This guy's 20 away. So it's 10 times, on average, further away. So the standard deviation, at least in my sense, is giving a much better sense of how far away, on average, we are from the mean. Anyway, hopefully you found that useful.